this. Thank you. Sorry about that. So you could compare this part to, you could directly compare this part to this part, but that's going to be a little hard to do here. So anytime I'm kind of like, it's a little hard to do, I might as well do the limit comparison test. In general, it's kind of a toss-up if you want to do the comparison test or the limit comparison test. There are times that the comparison test will work that the limit comparison test won't, and there's times the limit comparison test will work when the regular comparison test won't. So if you're doing a comparison and you try one of them and it doesn't work, you can always try the other one. So if I try the limit comparison test, we're going to look at the limit as n approaches infinity of 3n squared plus 3n plus 11 over n to the 5th plus 2n squared minus 7. So my original series divided by what we were comparing it to. So the 3 over n cubed. So does that make sense so far? Yeah, in the answer, did I just compare it to n squared over n to the 5th? Okay, so we're going to get that this is 3 as well, so it should be a similar argument, or I guess we're going to get here that it's 1, but I'm going to show you kind of where the argument probably comes from, so it's probably the same argument I made. If it doesn't clear it up, let me know, and I can pull up the answer sheet and do the algebra for you. So at this point, I'm going to do, so keep, change, flip, right? So I'm going to keep the top fraction, change to the bottom fraction. So 3n squared plus 3n plus 11 over n to the 5th plus 2n squared minus 7 times n cubed over 3. Okay, so I personally can look at this and say, oh, this limit is going to turn out to be 3 over 3, right? And the reason that I can do that is because I look at this and I go, okay, well, if I multiply this n cubed through, my highest term on the top is going to be 3n to the 5th. And if I take this 3, I'm going to have 3n to the 5th on the bottom. Since the highest powers are the same, this limit is going to end up just being the ratio of the coefficients. You could do L'Hopital's rule 5 times, right? So it's kind of up to you. But nobody likes to do L'Hopital's rule 5 times. But that you could get it by doing L'Hopital's rule 5 times. So just to do out the multiplication, I would have 3n to the 5th plus 3n to the 4th plus 11n cubed all over 3n to the 5th plus 6n squared minus 21, right? And then, again, I'm using that shortcut from back when you first learned limits. So before you learned L'Hopital's rule, right? This semester, we could do these limits in Calc 1. When we did them in Calc 1, you could divide everything by the highest power in the denominator, or you could remember from pre-Calc 1 that if you remember, limits as you go to infinity are really horizontal asymptotes. And so if you're just trying to find the horizontal asymptote, you're taking the ratio of the highest coefficients if the highest powers are the same. So that's how I get here that this limit is 3 over 3, which is 1. 1 is bigger than 0, so it's going to converge. Did that help? No problem. Other questions on this one? So you're allowed to have posted on Canvas, right, under handouts. I have the series handouts. So I think that's what I call it. Let me look. I can tell you what I called it. under handouts, there's a handout that says series tests reference sheet. And so I will give you that as well. Like, I'll post it with the exam. But if you wanted to print it out ahead of the exam to have it next to you, that's fine too. You can have that. So it's basically each of the series, and it tells, you know, it tells a little bit about the series and when it converges, when it diverges. So you're allowed to have that during the test. No problem. Other questions on this one? No? Okay. I'll record this time. Okay, so 3, was it 3A? Oops. 3B. Okay. And I skipped a page, so we'll just do it here. So 3B. Okay, so in problem 3, it's asking you to find the sum. Okay? So I'm going to give you a little hint. There are only 2 series that we can find the sum of. Okay? Those 2 series are geometric series or telescoping series. So if I actually ask you to find the sum of the series, you automatically know you're dealing with one of these 2 series. All the other series, we can just tell if they converge or diverge. We can't tell what the actual sum is. But on a geometric or telescoping series, we can actually say what the sum is. So the problem for 3B is the summation n equals 1 to infinity of 4 over n times n plus 2. Okay, so just looking at this, do we think it's a geometric series or a telescoping series? Yeah, it's going to have to be a telescoping series. Remember, geometric series are of the form, right? The summation, you might have some number a, but then you have something raised to the n power, r to the n power. I don't have that in this series, so it's got to be a telescoping series. Okay, so remember, telescoping series, when they're given like this, a lot of times we have to use partial fractions. So 4 over n times n plus 2, we're going to break that down into a over n plus b over n plus 2. And then I'm going to multiply by the n times n plus 2. So we get 4 is equal to a times n plus 2 plus bn. Does that make sense so far? Okay. So now you can find a and b however you want. I generally like to just pick, values for n. So if we let n be 0, I'd have 4 is equal to a times 0 plus 2 plus b times 0. So 4 is equal to 2a. Divide by 2. A is going to be 2. And if I pick n equals negative 2, I'd have 4 is equal to a times negative 2 plus 2 plus b times negative 2. So 4 is equal to negative 2b. Divide both sides by negative 2. So b is going to be negative 2. So my series, right, our original series, n equals 1 to infinity, is now of 4 over n times n plus 2 is really going to be the series n equals 1 to infinity of 2 over n plus negative 2 over n plus 2. Does that make sense? Okay. Questions so far? Okay, so at this point, essentially what we want to do is we want to think about the sum, and we want to kind of look at what's canceling out. So to do that, we kind of look at what we call like the nth sum. So this is going to be, so if I begin to write out the terms of this series, when we're starting at n equals 1. So when n equals 1, ooh, excuse me. So when n equals 1, we're going to have 2 over 1 minus 2 over 1 plus 2, right? When n equals 2, we're going to have 2 over 2 minus 2 over 2 plus 2, right? When n equals 3, we're going to have 2 over 3 minus 2 over 2 plus 3, right? And I usually write a couple of these out, so maybe we'll even go n equals 4. So we're going to have 2 over 4 minus 2 over 2 plus, or I really should have been 4 plus 2 technically, right? I should have. Plus, dot, 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 we're going to go up to 2 over n minus 2 over n plus 2, right? And then we would keep adding after that. So are we okay with that? Okay. So I'm going to work out what these are, right? So we've got 2 minus 2/3 plus 1 minus 2/4 plus 2/3 minus 2/5 plus 2/4 minus 2/6 plus dot, 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 plus 2 over n minus 2 over n plus 2 plus dot, dot, dot. Okay, and in a telescoping series, stuff is going to cancel out, right? So if you look, the negative 2/3 cancels out 2 things forward, the 2/3, right? The 1 isn't ever going to get canceled out, but the negative 2/4 cancels out the first term 2 forward, right? The negative 2/5, right, would cancel out the first term 2 forward, right? The negative 2/6 would cancel out the first term 2 forward from that. So does that make sense how like stuff is canceling out the things that are 2 forward? Yeah, okay. So, eventually, this term would get canceled out, right? And so what I'd really be left with is, I'm looking at, and I'm going on forever, so I'm really looking at the limit as n approaches infinity of this term, which I still have left over, which is a 2. This term, which I still have left over, which is a 1. And then basically this is kind of like the generic term that's left over, so minus 2 over n plus 2. And if I take that limit, I have 2 plus 1 minus 2 over infinity, or really this is just 2 plus 1, which is 3. And so that's what the sum turns out to be. So the sum turns out to be 3. Does that help for that one? Questions? No? Other questions that people have? Sure. Yeah, you're allowed to have the series sheet for the exam. Yep.
Can we go over number 4?
Sure, from From the test review sheet?
Yes, please.
Sure. So on this exam, it's all going to be series stuff. So there won't be like any like other stuff on this exam, right? Like the final exam will be comprehensive and cover kind of the whole course, but this exam it'll just be the series stuff. And then let's see. So basically, whatever number doesn't get canceled out in the beginning of the So, yeah, no, there's none of the three-dimensional shape questions. I'm trying to figure out what you're asking me, Robert. Whatever number doesn't get canceled out in the beginning of the telescoping series is going to be the opposite of the last term. So, it depends. It doesn't have to be... It depends on the particular problem. Like, yeah, like here, but in general, yeah. Because this never gets canceled out with anything. It could potentially be that, like, this number begins canceling out, like, the second number could begin canceling out the second numbers later on. So it's not that it's always like, oh, these are the first terms in these pieces, and then I'm going to be definitely left with the second term. You have to kind of look at each individual problem. This is generally what happens a lot of times. A lot of times you might have the first terms and then a second term left here, or you might have the second terms left here and the first term left here, but that's not a guarantee. It could be any part, so you really just have to see what cancels for each particular problem. Does that make sense? Yeah, it's not like a rule you can memorize, like, oh, this is always going to cancel out, or this is always going to cancel out. Other questions on this one before I go to 4? Okay, so in problem 4 asks us, is the following sequence absolutely convergent, conditionally convergent, or divergent, right? And it gives us this series, n equals 1 to infinity of -1 to the n minus 1, n to the -1/3. And so remember, when you're trying to do conditionally convergent or absolutely convergent or divergent, right? This is when I kind of drew that path, right? So you're given some series. Either you first look at the absolute value of the series, or you look at the original series given, right? So there's kind of two paths you can take for the answer. If you look at the absolute value and it converges, then that's when you have absolute convergence. If you look at the absolute value and it diverges, then you have to look at the original series. And if the original series converges, then it converges conditionally. And if the original series diverges, then the whole thing diverges. All right, so you could start by looking at the absolute value of the series, and then depending what happens, you might have to do more work. Or you could look by first starting at the original series. If the original series converges, then you have to look at the absolute value. If the original series diverges, then the whole thing diverges. When you look at the absolute value, again, it could converge or it could diverge. If the absolute value converges, then it converges absolutely. If the absolute value diverges, then it converges conditionally. Oops. Hopefully you guys know it says converges conditionally. So anytime you get conditional convergence, you're going to end up having to basically do two tests. So it's just the way, the only ways to get here to conditional convergence is you start with the absolute value, it diverges, you do another test, it converges, or you start with the original series, it converges, you do another test, it diverges. If you happen to have a series that is going to converge, it's going to be absolute convergence or converges absolutely. Then if you start with the absolute value, you sometimes get lucky and you can just do one test. Or if you have an inkling that your original series is going to diverge, you could just start with the original series and if it diverges, you're done. So it's kind of like, doesn't really matter which path you go. Probably about half the time you have to do two steps and the other half the time you don't. So with that being said, do we want to, here's my original series. Do we just want to figure out what the original series does, or do we want to look at the absolute value first? And there's no right or wrong answer. We just got to pick a way to do it so that to go forward with the problem.
Absolute value since there's the negative.
Okay, sure. All right, so if we look at the absolute value, so we're going to look at the absolute value. So that means we're going to have the series n equals 1 to infinity, the absolute value of negative 1 to the n minus 1, n to the negative 1/3. So the absolute value would get rid of that negative 1 part, right? N is positive, so we can drop the absolute value. So when I take the absolute value, I just get n to the negative 1/3, which this is really the summation n equals 1 to infinity of 1 over n to the 1/3. And so that's just a p series. P in this case is 1/3. 1/3 is less than 1, so what does it do? Yeah, it diverges. Okay, so basically we've gone down this track, right? We tried to the absolute value. We found that the absolute value diverges. So now we're sitting here. So we have to look at the original series, all right? So we're going to go back and look at the original. Whoops. Okay, so we're going to look at the original, which is the summation n equals 1 to infinity, negative 1 to the n minus 1, n to the negative 1/3. So what test would we want to do on that series? Yeah, it's an alternating series, right? Because I have negative 1 to this power. So we're going to look at the alternating series test. So remember, for the alternating series test, we have to look at the part that's not the negative 1. So that means this part here. And we have to ask ourselves first, is n to the negative 1/3 positive? Right, well, n are positive numbers. So if I take a positive number and I raise it to the negative 1/3 power, it's still going to be positive. Is it decreasing? So is n to the negative 1/3 decreasing? So if we think about it, we would have, this is 1 over n to the 1/3, right? And so as n gets bigger, right, those numbers keep getting smaller and smaller. So yeah, it's decreasing. And then the third thing we have to do is we have to look at the limit as n approaches infinity of n to the negative 1/3. So that's going to be the limit as n approaches infinity of 1 over n to the 1/3, which would be 1 over infinity, which would be 0. So that works. So the three things for the alternating series test are the pieces are positive, right, minus the alternating part, that they're decreasing, and that the limit turns out to be 0. So I've met all three of those qualifications. So what this is telling me is that the original series converged. Right? Oops, converges. That's fine. So that means I'm here, right? I looked at the original series. My original series converges. So that means my final answer is converges conditionally. Does that help with that problem?
Yeah, thank you. I can see it now how you flow through the map.
Yeah, no problem. Yeah, the map is helpful. Yep, it's an alternating series because you have -1. In this case, you have to the n minus 1. But it doesn't matter. As long as you have -1 to a power where that power allows you to go back and forth between positive and negative, then it's an alternating series. Yep. Sure, we can do 8a. Anybody have questions here on 4 before I do 8a? So it's not... It's not saying what it converges to, right? It's just saying that it converges. The only series you're allowed to say what something converges to is the geometric series and a telescoping series. Those are the only two where you're allowed to say, hey, this is what the sum is. So you know this goes to some number, but you don't know exactly what that number is. Okay, so 8a. Okay, so 8a says find a power series representation for f of x equals x to the 4th over 1 plus x cubed. Okay, so let me pull out, I should have pulled out my series sheet here before we started class. Okay, so this is one of the problems where I would be using that, like what we did last class, where I gave you that, here's the list of series, like known series, right? And so this is where, like, on the test, I would give you this information. So we know that the series, so this is from what we did last class. We said that the series 1 over 1 plus x is equal to the summation n equals 0 to infinity of -1 to the n x to the n. Right? Are we okay with that? So that I'm just pulling from last class. And so if you look at this, our series, we can really think of our series as x to the 4th times 1 over 1 plus x cubed. And if I compare 1 over 1 plus x cubed to 1 over 1 plus x, what's the difference? What's the difference between this and this? Yeah, I have an x cubed instead of an x. So our series, right, should be x to the 4th summation n equals 0 to infinity, -1 to the n. And then instead of an x to the n, we're going to have an x cubed to the n. So I really have x to the 4th summation n equals 0 to infinity, -1 to the n, x to the 3n. And then I can take the x to the 4th and I can pull it inside of that summation. I'm allowed to pull things in and out of the summation that don't have an n in them. So x to the 4th doesn't have an n in it, so I could stick it inside the summation. So this is going to be a summation n equals 0 to infinity of -1 to the n, x to the 3n, x to the 4th. And then I can combine those x's. So this is going to be the summation n equals 0 to infinity, -1 to the n, x to the 3n plus 4. So all the problems that are like find a power series representation, you're usually just tweaking in some way one of those series that I gave you already. Does that help?
So that would be our final answer?
Yep, that would be your final answer.
Okay, thank you.
No problem. Other questions?
I have a question about the exam, if that's okay.
Sure.
So is it going to be the exact same number of questions as it is on the...
No, there's more questions on the review sheet than I would ask you on the exam.
Okay. But it would still be relatively like the same format. We would get those questions for instance, and then the next ones. It's just the number of questions would be different.
I mean, it's probably pretty similar. I don't know that it's exactly like the same, but it's pretty similar. If you can do the stuff on the review sheet, you shouldn't have a problem with the stuff on the exam.
Oh, okay. Thank you.
No problem. Joshua, yeah, do you have one in particular, or is it just like you don't know when to use limit comparison? Like, okay, so, you can use limit compare. So let me find one first to do. Give me a second here. Okay, so what about... Alright, so what about determine if the following converges or diverges. I just found one in my notes that uses, that I use the limit comparison test to. Okay. So here's a series, right? So first off, I try to see if any other test will work before I try doing the comparison or the limit comparison test, right? So if you were to run down all the other series tests, right? The Divergence Series, the Divergence test, you're taking the limit of this as n goes to infinity. So just by looking at this, I can see, oh, if I take the limit of this as n goes to infinity, it goes to 0. So divergence test isn't gonna work. This is not a geometric series. It's not a telescoping series. It's not a P series, not an alternating series. I don't know how to integrate this, so I'm not gonna use the integral test. It doesn't really look like something that would work out well for the root test or the ratio test. Generally, a lot of times you're using the ratio or the root test when you're using the ratio test if you have a factorial. The root test you're going to be using if you have stuff raised to the n power. And so I don't have either of those things. So that kind of indicates, hey, it's probably a comparison test. In general, when I do a comparison test, I always try to, my first thing I do, whether I'm doing comparison, limit comparison, is I'm trying to figure out what to compare to. And my first pass, now it does not always work, but it works probably about 85% of the time, I would say, is to try comparing it to pick the biggest thing on the top and the biggest thing on the bottom. So we're going to try to compare to the summation n equals 1 to infinity of 1 is the biggest thing I had on the top, right? And the biggest piece on the bottom, so if you look, if I compare the square root of n with the, if I compare the square root of n with the cube root of n, square root of n is bigger. So the 2 square root of n part is the biggest part. And so this is really just the summation n equals 1 to infinity of 1 over 2n to the 1/2. The 2 is just a constant. So this is, so you can change the square roots to 1/2 and 1/3, but because they're added together, it's not a p-series. To have a p-series, it has to just be n to 1 power. You can't have that added together. So that's why we're doing the comparison test. We're comparing it to a p-series. So this here is a p-series. Our p is 1/2, which is less than 1, so this is going to diverge. So, questions so far? Okay, so now I know I'm dealing with either a comparison test or a limit comparison test. And so the next thing I do is I look at this and I go, okay, well, if this diverges, right, I need this to be bigger than this part, right? So do you think that this stuff here is going to be bigger than this stuff here? Yeah, no. This has more stuff on the bottom. So this is actually going to be smaller than this stuff here, right? So, okay. So that's an indication, well, let me try a limit comparison test and we'll see what happens. So I might get lucky that even though the regular comparison test doesn't work here, maybe the limit comparison test does. So the limit comparison test, what you do is you look at a ratio, you put on the top the original function, so 1 over, or the original series, so 1 over square root of n, cube root of n, right? So on the top is going the original, and on the bottom is going what you compared it to. So on the bottom here is going 1 over 2 square root of n. Does that make sense? Okay, so I have a fraction over a fraction in this case, so we're going to do keep, change, flip to make it look a little nicer. So I have 1 over 2 square root of n plus the cube root of n times 2 square root of n over 1. And so that's going to be the limit as n approaches infinity of 2 square root of n over 2 square root of n plus cube root of n. So if I try to find this limit, it's infinity over infinity. So I'm going to do L'Hopital's rule. So the limit as n approaches infinity. The derivative of the top, so I have 2 times 1/2 n to the minus 1/2. The derivative of the bottom is going to be 2 times 1/2 n to the minus 1/2 plus 1/3 n to the minus 2/3. Are we okay with that? Yes, no, maybe. Okay. So if you just try to take the limit again, you're going to be at like 0 over 0. So we're going to do a little bit of algebra work to kind of help us out here. So first off, what's nice, my 2 and my 1/2 cancel each other out. The other thing I'm going to do is, remember, this is really the limit as n approaches infinity. On the top, I have 1 over the square root of n. On the bottom, I now have 1 over the square root of n, plus I have 1/3 n to the minus 2/3. So if I multiply the top by square root of n and the bottom by the square root of n, I haven't changed anything. You have to, yeah, you could say that the top and the bottom have the same power, because minus 1/2 is the bigger power. So yeah, so you could do that. So I'm not canceling, I'm not canceling like this stuff with this stuff. I canceled this 2 with this 2. And then I canceled this specific 2 with this specific 2. Right? So I didn't cancel something from the top with the bottom. Everything I was canceling 2 pieces on the top or 2 pieces on the bottom. And so yeah, you could do what, I think it was Robert that said it. No, that's okay. It's the magic of typing a question, right? Half the time you type a question, then you're like, oh wait, I know the answer to it. So you could do what Robert said and say, hey, the power on the top is the highest power on the top, same as the highest power on the bottom, and just take the ratio of the coefficients. But if you didn't see that, the thing to do is to try to get rid of one of the top or the bottom. It's easier to get rid of the top, so that's why I'm going to multiply top and bottom by square root of n. And, oops. If I do that, I'm left with the limit as n approaches infinity. On the top, I have a 1. This first piece here, I have a 1. And then I have plus 1/3. So remember, this is n to the negative 2/3, and then this is n to the 1/2. So that's basically what we have going on here, right? I have n to the negative 2/3, n to the 1/2 multiplied times each other. And then I want to put them together. So this is really limit n approaches infinity of 1/1 plus 1/3. If you add those two together, you actually get n to the negative 1/6. And so I'm going to move this up a little bit. This is where I hate that, you can't see the whole board at once. So this is the limit as n approaches infinity of 1/1 plus 1/3 to the 1/6. And so now if I plug in infinity, I get 1 on the top, 1 plus 1/infinity. And so that's really just 1/1 plus 0. So the whole thing is 1. So I got a limit. The only thing you worry about in the limit comparison test is if your limit is bigger than 0. And 1 is bigger than 0. Okay, so you go through the whole thing, you get a limit. Even if that limit is infinity, it's okay. Infinity is bigger than 0. So as long as you get a number bigger than 0, okay, if you get a number less than 0, the limit comparison test didn't work for you, and you have to go back and either pick a new thing to compare it to or try a different test. But if you get something that is some number or infinity, in which case it's bigger than 0, then what it is saying is that your original series, so my original series here is going to do the same thing as this series did. So this series diverges means my original series diverges. If my original series had converged, then this series would converge, right? So since that's greater than 1, they both series diverge. Does that help with the limit comparison test? So since what we compared the series to diverged with the P series, and then we did the limit comparison, it would diverge, right? So yeah, so since the original series diverged, and then we did the limit, and we got something that was bigger than 0, then our series also diverged. If your original series, like if we had done a P series at the top and it had converged, and our limit was still bigger than 0, then our series would also converge. So the two, in the limit comparison test, the two series do the same thing, right? As long as the limit turns out to be something bigger than 0. And so, yeah, for this one, with this specific thing to compare it to, the limit comparison test did not work, or the regular comparison test did not work, but the limit comparison test did work. Yep. Questions? What do you mean by 1 over n is always a safe bet? You can compare it to 1 over n. Sure, I mean, we know what 1 over n does. 1 over n diverges. In general, though, I don't just try to pick random things. I really try to, when I'm determining what to compare it to, I really am problem specific. And I look at my original problem and I say, okay, I always try to pick the highest thing on the top and the highest thing on the bottom. So the biggest thing on the top is a 1. The biggest thing on the bottom is a 2 over square root of n. You could have done here a 1 over n, and you actually, if you did 1 over n, you probably, you might have been able to make the case that the regular comparison test would work. Maybe. But that's why here I picked the square root of n, because that was the biggest thing. You could have just done, you didn't have to take the 2, you could have just taken the square root of n part and it still would have worked out okay for you. Correct. The biggest thing on the top and taking the biggest thing on the top and the biggest thing on the bottom does not always work. But it works like 85% of the time. So it's always the place I start with. So I start with kind of, that's my general philosophy. Start with the low-hanging fruit, right? Try the thing that's easiest to do. The easiest thing to do is pick the biggest thing on the top, pick the biggest thing on the bottom. See if the direct comparison or limit comparison tests work out for you. If both of them don't, then try to compare it to something else. Yeah, I wouldn't worry about the other cases because there's not a ton of them. And most of the other ones that might not work out are just, they're really weird looking series to begin with. So, but 85% of the time I would say that picking the biggest thing on the top and the biggest thing on the bottom is going to work for you. Other questions? Other problems, things you want me to do. Sure, I can do 5A. Oops. Let's see. 5A. Just gotta go back to my review sheet. Okay, so find the radius and interval of convergence of the series. Okay, so summation, n equals 1 to infinity, 2 to the n, x minus 2 to the n over n plus 2 factorial. Okay, so any problem that asks you to find the interval and radius of convergence, the first thing you're going to do is the ratio test, okay, or the root test, but we're pretty much doing the ratio test. So we're going to do the ratio test. So the ratio test says, okay, take the limit as n approaches infinity of the absolute value of, we're going to take the n plus first term. So it's going to be 2 to the n plus 1, x minus 2 to the n plus 1 over n plus 1 plus 2 factorial, all divided by the nth term. So 2 to the n, x minus 2 to the n, all over n plus 2 factorial. So we're going to work out what this is first. So we're going to get the limit n approaches infinity. If I do keep, change, flip, right? So I have 2 to the n plus 1, x minus 2 to the n plus 1, divided by, this is n plus 3 factorial, times n plus 2 factorial over 2 to the n, x minus 2 to the n. Are you okay with that so far? Okay. So now, what we're going to do is, if I look at this, right, I can break up some of these. So I'm going to take a step to break these up. So 2 to the n plus 1 is 2 to the n times 2 to the first. X minus 2 to the n plus 1, right, is x minus 2 to the n times x minus 2 to the first power. This is all over n plus 3 factorial. If you notice over here, I have an n plus 2 factorial. So n plus 3 factorial is really n plus 3 times n plus 2 factorial. Times here I have n plus 2 factorial over 2 to the n, x minus 2 to the n. So some stuff's going to cancel out for me, right? The n plus 2 factorials are going to cancel. The 2 to the n parts are going to cancel. The x minus 2 to the n parts are going to cancel. And so we have the limit as n approaches infinity of, left on the top I have 2 times x minus 2. And on the bottom I have n plus 3. Are we okay with that? Or did I lose anybody at any of those algebra steps? Yes, no. We're good. We're not good. Okay. No problem. Yeah, simplifying the factorial is definitely so you just want to think about whatever the factorial is. You can take that first piece off and then just subtract 1. So that's all I did, how I got from n plus 3 factorial to n plus 3 times n plus 2 factorial. So I write down what this is and then I subtract 1. So n plus 3 minus 1 gives me that n plus 2 factorial. So at this point, I need to find this limit, okay? Now, the thing to notice is that on the top, there are no n's. So the top, we're talking about the limit as n goes to infinity. So the top is kind of acting like a constant in terms of there's no n's. And the bottom part here is going to go to infinity. So basically, what we really have is the absolute value of 2 times x minus 2 over infinity, right, if I were to kind of write it down. So again, I put in quotes around it because it's really kind of bad math notation to write divided by infinity. I do it a ton in this class, but I do want to just remind you, it is bad math notation. I just think that sometimes bad math notation actually can help understanding. And so I have some constant thing on the top divided by some ginormous number. So this whole entire thing goes to 0. So in terms of the ratio test, right, we always want the number, we're always comparing the number to 1, right? Remember, 1 is the tough luck case, like you're out of luck. And if we want it to converge, we want it to be less than 1. Well, 0 is always less than 1. So this is a little bit of a weird one. This is always true. And when you get something where it is always true, what that is telling you is that your interval of convergence, it doesn't matter what x is, so it always works. It's from minus infinity all the way to positive infinity. I can put any value of x in that I want, and this is going to converge. And the radius, so when we have the interval is from minus infinity to infinity, we say the radius is infinite as well. So the radius here is infinity. Questions? No problem. Step 3. So this step here. Are you asking how I got from step 2 to step 3, or how the stuff is that what you're asking? I just want to make sure I know what part to explain. Okay, so before we think about the n plus 3, n plus 2 factorial, let's think about like 7 factorial, right? So remember, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? 6 times 5 times 4 times 3 times 2 times 1, this stuff I just put in this blue box, that's really 6 factorial, right? So the idea is that I could write 7 factorial as 7, and then if I take 1 away from 7, so 7 minus 1 is 6, times 6 factorial. So it's like 7 times the next number down, which would be the 6 factorial. So does it make sense in terms of numbers? Okay, so we have the same thing, right? So we had an n plus 3 factorial. So if I were to start writing out what the pieces of this are, so I'm going to start with n plus 3, and then I'm going to subtract 1. So if I take n plus 3 and I subtract 1, I would have n plus 2. If I take n plus 2 and I subtract 1, I would have n plus 1. If I take n plus 1 and I subtract 1, I would have n. Oops, I want to make it bigger. And this pattern would keep going. Does that make sense? Okay, so this part here, right, if I box this part, that part there is really, I'm starting at n plus 2, so it's n plus 2 factorial. So n plus 3 factorial is really n plus 3 times n plus 2 factorial. So I think of it as like I peel off the first piece. So the first piece is n plus 3. I subtract 1. That's how I get n plus 2. And I have everything underneath it. So that's why I put n plus 2 factorial. Does that help? No problem. Other questions? Sure. Okay. 1D. Let me pull up what 1D is. Back to my review sheet. No, so a P series, when P is 1, that's 1 over n, and that diverges. So it only converges if P is strictly greater than 1. Okay, so 1D is the summation n equals 1 to infinity of 2 to the n plus 4 to the n over 7 to the n. Okay. So, again, I have this series. I'm trying to determine if it converges or diverges. And so the first thing that I want to do is I want to say, okay, well, it's not a geometric series because it's not just by itself. It's not a P series. It's not an integral test because I can't integrate that. It's not a ratio test. You might go, well, everything's raised to the nth power, so I could use a root test. But the problem is you have this plus sign here in the middle, so that kind of like, you don't really want to use a root test when you have two things raised to the nth power, but they're added. If they're multiplied, that's awesome, but added, no, I don't really want to do that. It's not really a ratio test. So you're left with a couple options. Okay, so there's two ways to go about this problem. One way to go about this problem is to say, okay, well, I'm going to use a comparison test, right? So you can definitely get this problem from a comparison test. So let's start with that way first. So let's try the comparison test, and then I'll show you there's a slick way to do it afterwards. So the comparison test. So compare, actually. Well, so we're going to compare. Okay, so if you use my like rule of thumb, right, which is, okay, we'll try comparing it to the biggest thing on the top and the biggest thing on the bottom, right? So the biggest thing on the top is a 2 to the n. The biggest, not a 2 to the n, 4 to the n. The biggest thing on the bottom is a 7 to the n. So this is really the summation n equals 1 to infinity of 4/7 to the n power. Yeah, so the problem with doing the root, or not the problem, doing the root test is not going to help you out a lot because, so remember the root test, we would look at the nth root of this, 2 to the n plus 4 to the n over 7 to the n. It would only help you out with the bottom because the top has a plus sign. So you would still have, on the top, you would still have the nth root of 2 to the n plus 7 to the n. So the most you can simplify this is to make this the nth root of 2 to the n plus 4 to the n over 7. And that's really like not any nicer. So that's why I wouldn't use the root test. Does that make sense? Yeah, so that's kind of like, that's the problem. That's the problem with the root test, right? You can't really figure out what that limit is. That limit is not a nice limit to figure out, right? If I had to figure out the limit of that, it's not nice. Like, I can't. You could root test the comparison you just did, but you don't need to. This is just a geometric series. And r is equal to 4/7. 4/7 is less than 1, so we know this converges. So I'm going to erase my root test part here. Okay, so I'm trying to do the comparison test. I pick the biggest thing on the top. I pick the biggest thing on the bottom. I end up with this geometric series that I know converges. And so if I try to do the direct comparison test, I need, since I have a series that converges, I need my series to be smaller. So is 2 to the n plus 4 to the n over 7 to the n, is that smaller than 4 to the n over 7 to the n? Yeah, no, right? Because the one on the left has more stuff, right? On the top, it has an extra 2 to the n. Okay, so I can't use a direct comparison test. I could try the limit comparison test, right? So, no. So we could try the limit comparison. So we could look at the limit as n approaches infinity. So remember, it's the original, so 2 to the n plus 4 to the n over 7 to the n, divided by 4 to the n over 7 to the n. Right? And if we do keep, change, flip, right, this is going to become the limit as n approaches infinity of 2 to the n plus 4 to the n over 7 to the n times 7 to the n over 4 to the n. So my 7 to the n's cancel each other out. And I'm left with the limit as n approaches infinity of 2 to the n plus 4 to the n over 4 to the n. That's not the nicest limit to figure out either, right? If you put in, you end up with infinity over infinity. If I do L'Hopital's rule, I end up, the limit n approaches infinity. Derivative of the top is going to be 2 to the n ln 2 plus 4 to the n ln 4 all over 4 to the n ln 4. So my limit didn't really get any better, right? And I still just have infinity over infinity. So I still can't really figure out what is going on here. So that's kind of sad, right? So here's one where just taking the biggest piece on the top and the biggest piece on the bottom didn't actually help us out. It didn't help us figure out what happened. The direct comparison test didn't really work. The limit comparison test, I can't really get anywhere because I get this limit that I can't really figure out. So it's a mess, right? So that kind of means, we probably didn't pick the right thing to compare it to. Okay, so let's start again. So we have the summation n equals, was it a 1? Yeah. N equals 1 to infinity, 2 to the n plus 4 to the n over 7 to the n. Okay, so I'm going to pick something else to compare to. So n equals 1 to infinity. So I'm going to keep the 7 to the n on the bottom, right? The 7 to the n on the original, like there's nothing else there. There's nothing else for me to do. My problem, right, was that I picked just 4 to the n on the top, and that converged, but then I couldn't say that my original function was less than it. So what I'm going to do this time is, if you notice, my top has 2 pieces. I'm going to replace this 2 to the n with another 4 to the n. So I'll take the biggest thing on the top and I'll replace everything on the top with it. So let's compare to 4 to the n plus 4 to the n. So this would be the summation n equals 1 to infinity of 2 times 4 to the n over 7 to the n. Or the summation n equals 1 to infinity of 2 times 4/7 to the n. So it's still a geometric series. R is still 4 over 7. That's still less than 1. This still converges. Right. So I still get a pretty nice series to compare it to. So now I want to know, is 2 to the n plus 4 to the n over 7 to the n, is that less than 4 to the n plus 4 to the n over 7 to the n, right? So that's kind of where I originally started. So what do we think? Is 2 to the n plus 4 to the n over 7 to the n less than 4 to the n plus 4 to the n over 7 to the n? Yeah. So is it? Yes. All right. So then our series n equals 1 to infinity of 2 to the n plus 4 to the n over 7 to the n also converges. So that helped me out, right? I had to pick something different to compare it to. So I got 4 to the n plus 4 to the n over 7 to the n by, I kept the bottom the same because there was just one thing in the bottom. And so I kept the one thing in the bottom the same. What I did here was, rather than just take the biggest part, which is what I did on this previous page, right? I just took the biggest piece from the top. This time I took the biggest piece from the top and I replaced all the pieces in the top with the biggest piece in the top. So I got rid of the 2 to the n, right? I got rid of the 2 to the n and replaced it with a 4 to the n. So basically I'm saying, well, this 2 to the n kind of was a problem before, so maybe if I wipe it out and I replace it with a bigger, something with this biggest thing from the top, maybe it'll help me out. So does that answer the question about where I got 4 to the n plus 4 to the n from? And then I'll talk about how it turns into 2 times 4 to the n. Okay. So think of it like I have 4 apples plus another 4 apples, or this is like one term, right? So like, just like if you have x plus x, that's 2x. This is acting like my whole entire x, right? So I have something plus something, which means I have 2 of that same somethings. Does that help with how it turned into 2 times 4 to the n? No problem. Okay, so at the beginning, right? And so I should say, this here is how I did it on the review sheet, right? I pulled it up while we were doing stuff. So this is how I did the answer on the review sheet. There is a slicker way to do this problem. And so the slicker way is to notice that at the very beginning, I actually could have rewritten the series. So I had n equals 1 to infinity of 2 to the n plus 4 to the n over 7 to the n. And I actually could have broken this up, so into n equals 1 to infinity of 2 to the n over 7 to the n, plus 4 to the n over 7 to the n. And I'm allowed to break it up because there's one thing on the bottom, but multiple things on the top. And then in that case, I could actually make this into 2 series. So the series n equals 1 to infinity of 2 to the n over 7 to the n, plus the series n equals 1 to infinity of 4 to the n over 7 to the n. Or the summation n equals 1 to infinity of 2/7 to the n, plus the summation n equals 1 to infinity of 4/7 to the n. Right? So I'm allowed to actually break this up into these 2 series. Both of these series are geometric, right? This first one is geometric. R equals 2/7, that's less than 1, so this one converges. This one is also geometric. R equals 4/7, which is less than 1, so it also converges. Right? So if I have 2 I almost lost all my papers here. If I have 2 series that are both convergent and I add them together, I get a convergent series. So therefore, our series 2 to the n plus 4 to the n over 7 to the n also converges. So that's kind of the slick way to get it, is to notice, oh, I could have broken it into 2 series and both of those series happen to converge themselves. Does that make sense? It is easier than the first way, but you have to see it, right? So obviously, like, I saw it this time, like I looked at it and I was like, oh yeah, I could split into 2 series, but probably the first time I did it, when I did it the way I did it on the review sheet, I probably didn't see that I could split it into 2 series. So it's kind of like, it's easier, but as long as you see it, right? But if you don't see it, it's not easier. Other questions? Other questions on anything else? Sure, like any particular one? Find a power series for, what about, here's one from the homework. X cosine pi x. Okay, so the thing we want to remember is that the series for the cosine of x, okay, is the summation n equals 0 to infinity. It's negative 1 to the n x to the 2n over 2n factorial, right? So rather than an x here, right, I have pi x. So this is going to be, so we're going to write the series representation for the cosine of pi x. So we're still going to have an x out in front for that original x, and then the cosine of pi x is going to be the summation n equals 0 to infinity of negative 1 to the n, and then instead of an x, we have a pi x. So we're going to have pi x to the 2n over 2n factorial. So this is going to be x summation n equals 0 to infinity. We're going to have, so if I kind of do a little bit of algebra, negative 1 to the n, pi to the 2n, x to the 2n, all over 2n factorial. And then I can take that x that's sitting outside of the summation and bring it inside. So the summation n equals 0 to infinity, negative 1 to the n, pi to the 2n, x to the 2n times another x, all divided by 2n factorial. So this is going to be the summation n equals 0 to infinity, negative 1 to the n, pi to the 2n, x to the 2n plus 1, all over 2n factorial. Does that make sense? No problem. Other questions? I just finished it this morning, so I saw right before class it finally finished uploading, so I'll put the link up there before the day is done today. I did finally do all the videos for the problems from chapter 11 that you guys wanted, so all the series problems. So up on the homework page, I'll put a link to the YouTube video. All of the questions you asked for all of the sections are all in one video. So I'll put that video up. So in case you want to go watch any of those problems, all the ones you guys kind of put in the self-assessment, I talked through all those different problems. So if you're looking to hear explanations of some of those problems, if you asked about some of them, they'll be up there. I will note that people asked me about in section 11.6, 11.6, number 10, where the problem that I typed is not the problem that is the answer. The problem I typed was wrong. I don't know why I put an exclamation point in it to make it a factorial. It shouldn't be a factorial, and putting a factorial there makes it a terrible problem. It's terrible to do. So I just put in the video, hey, that's terrible, and I would never ask you to do that. So I didn't actually do that problem out because it's really horrendous. The problem that is in the answers for section 11.6 number 10, that is the problem I meant to give you. So just be aware of that. If you're like, oh, I want to see what the answer to that problem is, you're not going to find the answer to the problem in the actual homework I typed. So, any other questions? What was the problem that had a series in the series? I don't know if I know what you're talking about, Lane. Was it? Oh, was that the problem that had a series in the series? No, it was there was a factorial. It was like a polynomial with a factorial, so it was just really ugly. I don't know the problem you're talking about. It might have been, no, I don't know if I know which one you're talking about off the top of my head. Any other questions? No. Okay. Then in that case, if you guys are studying and you have questions, let me know. Otherwise, I will see you all on Thursday for the test.
Thank you, Professor. Have a
No.
nice day.
Thanks, you too.